Hello all, I am Praveen Kumar and my friend Harbabu. We are going to discuss about an improved Canny edge detector. This is an IEEE transaction paper which was published in 2014. The main motivation behind this paper is to reduce the problems of traditional Canny edge algorithm. This traditional Canny edge algorithm mainly has two problems. The first one is it is very sensitive to the noise, so that we are going to lose the weak edge information. And the second one is it shows poor adaptability in thresholding. So these two problems were reduced by the improved Canny edge detection algorithm. Firstly, I am going to discuss about traditional Canny edge algorithm, and after that we are going to learn and deeply discuss about improved Canny edge detection algorithm. There are 4 steps are there in the traditional Canny edge algorithm. The first one is image filtering. In this first step, we are going to smooth the image with the Gaussian function. This Gaussian function is a 2-dimensional Gaussian function, and the property of this Gaussian function is it just removes the noise and it gives the information about the edges. So the equation for this one is this one, equation 1, and the sigma stands for in this equation 1 is Gaussian filter parameter. This sigma controls the extent of smoothing image. That means if sigma is large, the smoothing is also in large manner. Second step is image gradient calculation. This traditional Canny edge algorithm uses the 2x2 neighboring area to find out the image gradients. So the first gradient in x direction and gradient in y direction equations are these two, equation 2 and equation 3, and the corresponding operators are gx and gy. So using these two equations, we are going to get the gradient magnitude and gradient orientations. By using these 2x2 neighboring area, we have some disadvantages. Those are discussed in further slides. So by using these two equations, we are going to find out the gradient magnitude and orientation of the image gradient. Those equations are 5 and equation 6. Third step is non-maximum suppression. Firstly, in this step we are using 3x3 neighboring area. Consider a 3x3 window, and let us assume we are at the middle pixel, and definitely there exist 8 directions, and just keep any one direction and consider the values, interpolated values to the middle pixel value. If the middle gradient pixel value is greater than the remaining 2 interpolated values, then we can mark the middle pixel as edge point, otherwise non-edge points. Just look into this image. 6 and 7 are less than the 8, so that 8 can be marked as edge point, and we can neglect the 7 and 6 values. The fourth step is checking and connecting edges. That means we are going to check the edges and also connect the edges. In this step, we are using 2 threshold values, high threshold value and low threshold value. If the gradient magnitude is greater than the high threshold value, we can mark that point as edge point. If the gradient magnitude is less than the low threshold value, we can mark it as non-edge point. And another case, if the gradient magnitude lies between these 2 threshold values, then those points can be marked as candidate edge point. Look into this image. There is one edge greater than the high threshold value, so that we can name it as edge, and there are no edges below the low threshold value, and there is one edge exists between these 2 threshold values, but this is not connected to any high edges, strong edges, so that I am removing those edges also. So I marked as not an edge. So using this step we can find out the edges. So these are the 4 steps in the traditional Canny edge algorithm, and after that we are going to discuss about some of the problems related to this traditional Canny edge algorithm. I already mentioned in the previous slide, mainly it has 2 problems. First one is it is very sensitive to the noise. By using the 2 by 2 neighboring area, it doesn't give the information about the 45 degrees and 135 degrees orientations edges information. That means if the edge gradient is in the direction of 45 degrees and 135 degrees, we are going to lose those edge information, and it is very sensitive to the noise. This is the first problem. And the second one is, in the last step we are using 2 threshold values, that is high threshold value and low threshold values. In this traditional Canny edge algorithm, those 2 threshold values are manually fixed by looking at the images, but this is not applicable to some of the cases. Just assuming if an image contains a rich edge information, in that case, if we are using the fixed values, we are going to lose some of the information about the edges. So this is the second problem. To reduce this problem, we are going to keep on modifying these threshold values by using some of the gradients and magnitudes. Those points discussed in the further slides, and those things are also discussed by my friend Haribabu. And thank you.
Hello everyone, I'm Hari. Now I will discuss improved Canny edge detection algorithm. The first step is to find out the image gradient. Professor Wang uses 3 by 3 Sobel operator and Prewitt operator instead of using 2 by 2 neighboring area operator, so that more edge information was preserved. Later, Professor Livingston proposed a novel edge detection algorithm based on the Newton's law of universal gravity known as gravitational edge detection algorithm. It is based on the gravitational force between two bodies, given by the formula G into m1 m2 by r12 magnitude whole square into r12 unit vector, where G is the gravitational constant, m1 m2 are the masses of the bodies, and r12 is the vector from body 1 to body 2. The gravitational force on a point in dark zone is smaller than the gravitational force in brighter zone, even though they have the same gradient. So it have a less relevance to the gradient changes in dark zone, which results loss of weak edge information. To overcome the difference between bright zones and dark zones, this paper introduced the gravitational field intensity, given by the formula G into m divided by magnitude of r whole square into r unit vector, where m is the mass of the pixel. The total gravitational field intensity on one point in the image is a combination of gravitational field intensity produced by surrounding pixels. It is known as the image gradient. If this intensity is greater than particular pixel value, then it will be considered as edge point. In order to find out the gradients in x direction, y direction using gravitational field intensity formula, we consider a 3 by 3 neighborhood window in which 8 neighborhood pixels are placed around center pixel I, j, and named like in a clockwise manner m1, m2, m3, m4, like that. So the gradient in x direction ax of I comma j equal to some combination of all gravitational field intensities. So the gravitational field intensity for m4 pixel is g into m4 divided by magnitude of r whole square into r vector divided by magnitude of r. Here magnitude of r equal to 1 since the distance between these two pixels is 1, and we are finding the gradient in x direction, so r vector will be I. So the total gravitational field intensity for m4 pixel is g into m4, and since it is in a positive direction it will be plus sign. Similarly for m3 pixel, the distance between these two is square root of 2, so g into m3 divided by root 2 whole square into root 2, and in x direction, so r vector equal to I. So, and it is moving forward direction, so plus sign. So in this way you can find out the gradient in x direction for all neighborhood pixels. Similarly, we can find the gradient in y direction like that. For m2, g into m2 divided by r square, magnitude of r square into r vector divided by magnitude of r. Here magnitude of r is nothing but the distance between two pixels is 1. So magnitude of r equal to 1, and we are finding gradient in y direction, so it is r vector equal to j, and it is in forward direction, so plus sign will be assigned. In this way, for adjacent pixels in vertical direction, it will be distance will be 1, and diagonal directions the distance will be square root of root 2. In this way we can find out the all neighborhood gravitational field intensities and sum over them. So the total gradient magnitude is nothing but square root of gradient in x direction whole square plus gradient in y direction whole square. The direction of gradient is nothing but tan inverse of gradient in y direction divided by gradient in x direction. The 3 by 3 mask operators for finding image gradient using the gravitational field intensities are given as follows. If the gx is the gradient intensity in x direction and gy is in y direction. The second improvement is adaptive threshold selection. Unlike in traditional Canny detection algorithm, here two adaptive threshold selection methods were introduced for two kinds of typical images. Basically, the edge is the region which has larger gradient magnitudes. So edge can be a pixel is an edge or not based on a particular gradient magnitude value. So the selection of threshold has greater relationship with the mean of gradient magnitude and standard deviation. The two types of images are images with less edge information and images with rich edge information. The first one is threshold selection method for images with less edge information. In this image, the gradient magnitude of majority of the pixels are located in small range values. So the mean and standard deviation are relatively small. The upper and lower threshold value for the pixel values can be find out through its mean and standard deviation. The higher threshold value is nothing but average value of the whole image plus k times into standard deviation of the whole image, and the lower threshold value equal to higher threshold value divided by 2. With these two thresholds we can able to detect and connect the edges. Here k is a constant which depends on the standard deviation of the image. If the standard deviation is very small, we approximate the k value equal to 1.6. If the standard deviation is very high, the k value will be taken as 1.2. The second method for images with rich edge information. The image's gradient standard deviation is relatively large here since each part of the image is inconsistent. So we consider the pixels as a non-edge pixels which are less than lower threshold value. The lower threshold value is 15 to 20% of average of the whole image, and divide the total image patches into n cross n size and find each threshold value where th is the upper threshold value of that patch equal to average value of that patch plus k times into standard deviation of that patch. So we were able to find the higher threshold value and lower threshold value for each patches, and we can detect and connect the edges using common low threshold value and unique upper threshold value for different patches. These are the experimental results under microscopic view. The first one is a cell image which have less edge information in the microscopic view. The second figure is edge information obtained through traditional Canny edge algorithm. The C and D figures are edge information obtained through Sobel and Prewitt operators, and the final one is through improved edge method of less information edge. These are the experimental results for rich edge information image. The first one is the tire image in wide range view, and the second one is the edge information obtained through traditional Canny edge approach, where C and D is edge information obtained through less edge information method threshold selection, which are not good. And the final one is edge information obtained through threshold selection of rich edge information method. These are the references taken to read this paper. The detection results of the improved Canny edge detection algorithm are superior to the Robert, Sobel, and other traditional Canny edge operators, but it is relatively slow to compute, which needs to be further improved. Thank you.